Hello, everyone. Once again, thank you so much for time. Today, I'd like to continue on our discussion on multiple access. Earlier on, I have defined what is multiple access. Multiple access is defined as many users share one common resource effectively. So this is the definition of multiple access. Our topic for today's discussion is direct sequence and frequency hopping spectrum. Spectrum is one form of multiple access. Spectrum allows multiple users to share the frequency effectively. In spectrum communication, there are actually two types. One is direct sequence, another type is frequency hopping. For today's discussion, I'm going to focus more on direct sequence spectrum. This is my email. If you have any question regards on today's discussion, please drop me an email. Before I continue, I'd like to urge you guys to support this channel by pressing the like and subscribe buttons. Please also turn on your notification bell in order to receive more information from this channel. Guys, if you learn something or you recall something from your school, please help this channel by pressing the like and subscribe button. Thank you so much. A spectrum communication system transmits information over a much wider bandwidth than necessary. This means that bandwidth is not really proportional to data. In a spectrum, they actually purpose increase their bandwidth to send the same amount of data. So this is a definition of spectrum. They use more bandwidth to send the same amount of data. There are two types of spectrum techniques. First is the direct sequence spectrum, which denoted as DSSS. Each transmitter is given a special code known as chipping code. Okay, so this special code is known by the transmitter and receiver only. This code is actually multiplied with the original message before transmission. So they do a form of encryption by multiply the code with the message before it actually transmit. The receiver use the same code to retrieve the original message. Okay, so this is the first type of spectrum, direct sequence spectrum. Next, we have frequency hopping spectrum. Transmission switch across multiple narrowband frequency in a presumed random manner. Okay, so for FHSS, okay, they use very narrow band. They are given a much bigger bandwidth, okay, but they transmit very little bandwidth. Okay, so the sequence of transmission frequency is actually only known by the transmitter and receiver only. Okay, so let's take a look on this frequency hopping spectrum first. Okay, the transmitter repeatedly change or hop around the carrier frequency in a sequence that only the receiver know. Okay, so let's take a look on this animation. Okay, for example, okay, you can see from here, they jump at a different channel. Only the receiver know how the transmitter put the message, and the receiver jump in the same sequence to retrieve back the original message. So this is frequency hopping spectrum. Next, we have this direct sequence spectrum. Okay, for direct sequence spectrum, the frequency spectrum is spread by modulating the carrier with a high chip rate prism noise code to obtain a signal with a wide bandwidth. Okay, so this is the original data and the original bandwidth they actually occupy. When they actually utilize this direct sequence spectrum, they actually occupy the whole bandwidth to send the same amount of data. Okay, so later on, okay, you will realize how they can actually achieve this. Instead of using words to describe what is direct sequence spectrum, I have decided to use this example to show it to you what is direct sequence spectrum. Okay, for example, there are three users. The three users transmit at the same frequency and also at the same time. I'm going to show it to you. How can we recover the individual user data, okay, without knowing how many users are transmitting and what are the rest of the user data? I'm going to show it to you. How can I recover user 1 data, also user 2, and also user 3? Okay, let's start by this example. For example, user 1 has a data of 00 to send to the recipient. They have a Splat code of 0101. Okay, so this is the Splat code, a unique Splat code that is given to user 1. Okay, since the Splat code is 4-bit, okay, I actually duplicate the message 4 times as shown in red. Okay, as for another bit of data, I also duplicate 4 times. Next, this will be the Splat code. Okay, Splat code is 0101. After that will be another 0101. So what I'm going to do is I'm going to do an exclusive OR. Exclusive OR means that if the 2 bits is the same, okay, I will have a 0 at the output. If they are different, I will have a 1 at the output. So they are same, so therefore I have a 0. Different, I have a 1. Same, 0. Different, 1. Same, 0. Different, 1. Okay, so this is the message that the user 1 will be sending over to the recipient. Okay, you can also see over here, the user 1 actually has only 2 bits of data, but now they actually send 8 bits of data. So this is what we have described earlier on. So instead of 2 bits, they actually spread to 8 bits of data, which means that they actually require more bandwidth to send this data over. So this is the meaning. Okay, next, let's come to user 2. User 2 have a data of 10 to send, and is given a Splat code of 0011. Okay, so again, my data 1, I duplicate 4 times. Same for another data 0, I duplicate 4 times. This is a Splat code 0011, 0011, and again, I do an exclusive OR. Okay, so this is the user 2 data that will be sending over the air. Next, for user 3, again, user 3 has a data of 11 to send and is given a Splat code of 0000. Okay, I guess you know why I illustrate this example, because everything become 1 after exclusive OR. So this user 1, user 2, and user 3, they send the message using the same frequency and they actually transmit at the same time. So let's define this. When the message is 0, okay, I will use a +1 volt to draw the waveform. When the message is 1, I will have a -1. Okay, so this is 01010101, which is on here, 01010101. Okay, so this is a message. Again, like what I mentioned, when the message is 0, okay, I have a +1 volt. When the message is 1, I have a -1 volt. So you can see that the waveform actually become a toggle 10101010. Next, for user 2, okay, the user 2 message is 11000011. So this is 11000011. Okay, again, when the message is 1, okay, I use -1. And when the message is 0, I use a +1. And this is how I get the user 2 waveform. Next will be user 3. Okay, user 3 is all 1, so will be a flat -1 line. Okay, so this is the signal that sent over. So what I need to do is I combine all the 3 signal. For example, this is +1, -1 become nothing, become -1. So therefore my outcome is -1 here. -1, -2, -3. So the outcome is -3 volt. Plus, -1, therefore my outcome is +1 volt. Minus, plus, nothing, -1 volt. Plus, minus, +1 volt. Minus, positive become nothing, minus become -1 volt. Plus, minus become -1 volt. -1, -2, -3, and the final outcome will be -3. Next, this will be the composite video that will be sending in the air. Okay, so this waveform is actually what I have obtained from this outcome here. So this is -1, -3, +1. So you can see from here, -1, -3, +1, -1, +1, minus, minus, and then -3. Can you see here? So now I'm going to show it to you. How can I recover user 1 code? Okay, so I know the user 1 spread code, okay, because I want to receive user 1 spread code. And when I actually know the spread code, okay, I actually can recover back the original signal that is sending by the user 1. Okay, again, when it's a 0, I will use a +1 volt to denote. When it's a 1, okay, I will use a -1. So you can see from here, this is 0, 1, 0, 1, 0, 1. Again from here. Okay, so this is the spread code that is for user 1. Okay, what I need to do is basically I multiply. Okay, so the composite signal that is in the air, what I need to do is I multiply this signal. -1 +1 become -1. -3 -1 become +3. +1 times 1 become +1. -1 -1 become +1. +1 times 1 become +1. -1 times -1 become +1. -1 times +1 become -1 volt. -3 multiplied by -1 become +3 volt. Okay, so next, what I need to do is I add all these, okay, because I know the spread code is 4-bit. So I will add the 4 bits of data together. So -1 become 2, 3, 4. So I actually obtain 4 volt. And because the spread code is 4-bit, so I do a divide by 4, which I obtain 1 volt. You can still remember for 1 volt, the data is actually 0. Okay, same over here. So what I need to do is basically I add them all together, +1, +2, -1 become +1. Okay, +3 become 4 volt here. So again, it's 4-bit of spread code. I do a divide by 4. So I actually get 1 volt. And again, 1 volt means it's a data 0. So now I can actually recover my user 1 data, which is 0, 0. Okay, if you still remember here, this is the user 1 sending the data of 0, 0. Okay, and then there are 3 users sending together. Okay, and I actually can recover back the user 1 data without knowing how many users they are, without knowing what are the user data. This is how I recover user 1 data. For user 2, okay, so again, this is the composite video in the air. Okay, what I'm going to do is the same thing. I use the composite video, I multiply by the spread code of user 2. User 2 spread code is given is 0011. So this is 0 is +1 volt. Okay, and then when it's message 1, I actually have a -1 to indicate it. So this is the spread code that is given to user 2. Okay, again, I'm going to multiply them. -1 multiplied by positive become negative. -3 positive become -3. +1 multiplied by -1 become -1. Minus multiplied by minus become +1. Okay, let me do this first now. So -1, -4, -5, okay, and then become -4. So this is -4 volt. Again, I need to divide by 4 because I have 4-bit of spread code. And what I actually obtain is -1. Okay, so when it's a -1 volt, I know my data is actually equals to 1. The same wise on the other side of a user 2 data. Okay, again, I'm going to multiply them. Okay, +1 multiplied by +1, I get a +1 volt here. Okay, minus positive become -1 volt. -1 volt times by -1 volt become +1 volt. -3 -1 become +3. Again, I add them all up. So plus minus nothing. +1 + 3 become 4 volt. So again, it's a 4-bit spread code. So I divide by 4. So I actually get a 1 volt. Okay, 1 volt simply means that is a data 0. So now I know my user 2 data 10. Okay, let's verify the result. Okay, user 2 is 10. Okay, can you see over here? What I did is I just know my Splat code. I actually can recover user 2 message. Same wise for user 3. Okay, user 3 is much more easier because I purposely all 2 plus 1 book, okay, because the Splat code is all 0. Okay, so this is -1, -3, plus 1 book, and -1 book here. So again, I add them together, minus become 4, 4. This cancel each other, become -4 book. I do a divide by 4, again, because the Splat code is 4-bit. So it's -1 book. So when it's -1 book, I know my data is 1. Same wise over here. So this is 1, this is -1, this is -1, and then this is -3. Again, I add them. These two cancel each other. So I get -4 book. Again, I need to divide by 4 because Splat code is 4-bit. So I get -1 book. So -1 book, I know my data is 1. Okay, so let's verify user 3 data. Is it 1, 1? Yep, it's 1, 1. So I actually also successfully recover back user 1 data, user 2 data, and also user 3 data. With this, I'd like to end our discussion. Please help to like and subscribe. Thank you so much.